Okay, so I'm going to talk about some our most recent experiments with our ultra-cold plasmas, and really the focus in my lab is trying to get at the implications of strong coupling, because we look at the ions, whereas you've heard a lot about the electrons mostly, and the ions are actually the more strongly coupled component, and the strong coupling really changes a lot of the parameters that are very commonly understood and used in normal plasmas, and so that's very interesting. And the one I'm going to emphasize the most here is the Landau-Spitzer time. You've heard, of course, that there are lots of other interests in ultra-cold plasmas, and just without looking at strongly coupling, there's the way the plasma expands, there's the various collisions between the components, recombination, collective modes, and instabilities have all been looked at so far. The aspects that are really depend on strongly coupling or the different ways of looking at it. You can really think of this as a paradigm many-body system for studying strongly coupled physics. And what's really nice in our systems are that we have two components, both electrons and ions. And the electrons can be kind of close to the strongly coupled regime too, so that has some implications. And the kind of things that will show the strong coupling are the equilibrations, establishment of correlations, and transport properties of the plasmas. Already some connections between these ultra-cold experiments have been recognized, particular to high energy density and warm dense matter physics, which are also laser produced plasmas. They show very similar dynamics to some of the regimes in which we study. There's even an application's been proposed and is being explored, which is using ultra-cold plasmas to create bright charged particle beams. I never expected there would be any applications to come out of this research when we started it, that's for sure. And this is the area I'm going to focus on today. And here's my outline. I'll give you, I won't have to go through the creation very much. I'll spend a little more time talking about the strong coupling. I want to make sure that that's familiar to us all. And then we'll talk about the breakdown of classical plasma physics behavior. I'll talk a bit about kinetic energy oscillations and then the Landau-Spitzer time. I'll skip over the creation rate, just except to say that we work with strontium atoms, and that's actually not the normal, Scott works with calcium, but going to the alkaline earth systems brings in a lot of new things. And I recognize that a lot of different people have contributed to this on the theory front and the experimental front. The exchange of ideas has really helped this field. Again, so here's this figure that we've seen probably a million times here. And what I want to emphasize again is how we cross into the strongly coupled regime. And lots of times you run into a plasma physicist and they'll say this isn't even a plasma over here because plasmas can't exist. They're not stable. Systems want to become solids and liquids in this regime, or actually recombine to gases and solids and liquids in this regime. But the strong coupling actually has a lot of implications. You can find strongly coupled plasmas in the interior of gas giant planets, or the interior of more exotic astrophysical elements as well. The strong coupling is parameterized by this Coulomb coupling parameter, the ratio of the Coulomb energy for nearest neighbors to the thermal energy. A is the interparticle spacing that pops up in a lot of these formulas. And really, here are some images of some other strongly coupled systems. Here are pure ion plasmas from NIST and Boulder. Actually, you're imaging individual ions here. And these systems have been cooled to where gamma is greater than 200 or so. And the system has frozen into a Wigner crystal, a regular lattice with long-range spatial order. And this arrangement minimizes the potential energy. So this establishment of order is really what's getting at the heart of strongly coupled plasma physics. And that really changes the behavior of systems compared to a more gaseous system, which is a normal plasma. So as Francis mentioned, if you get gammas just order of greater than about 1 or so, you get liquid-like correlations. So those are short-range spatial correlations, but no long-range order. But as gamma gets on the order of 200 or so, you expect long-range order to come in as well. And there's been a lot of interest from theoretical groups working on these systems as well, because, as I said, the physics does connect to these astrophysical systems, but it's hard to do experiments on them. And also inertial confinement fusion as well. In the first moments of that a pellet is imploded, strongly coupled physics can come into play there as well. So there's a lot of theoretical effort put into understanding systems like this, and they can actually use their codes to test our systems. So I think that's generated some of the interest. So by using strontium, this is what I wanted to point out, we get a very nice probe that's a little different than the one that Steve had mentioned, whereas he's detecting charged particles that come out of the plasma, we can look at the ions directly when they're in the plasma because the strontium ions have transitions that are accessible. So the level structure looks a lot like rubidium neutral. So we get a double S 1/2 to a doublet P 1/2 transition at 422 nanometers. So we can take absorption images of the plasma, and those are really nice because we can absolutely calibrate them and get the density very, very well. But we also have done a lot of work now on fluorescence of the plasma, and that can actually get us a little better signal to noise and also can allow us to get around a lot of effects, such as we don't have to average over density anymore. When we take fluorescence from a sheet excitation, for instance, we can really, in our image, identify fluorescence, and this will be coming from just a very small region of the plasma with no density averaging, whereas for an absorption image, you have to integrate along the line of sight. So that's actually very important for quantities that are density dependent to be able to resolve them. But in either of those configurations, we get most of our information from looking at the spectrum of the excitation. So here for absorption, if we look at the absorption spectrum as we vary the frequency of that probe beam, we can see that on resonance we get the strongest absorption, and obviously off resonance it drops off. This is just the ion absorption spectrum. And for our conditions, it turns out that it's Doppler broadened. It's significantly broader than the natural line width. So the width can be directly mapped onto the RMS velocity along the direction of the laser beam. If the system is thermal, then we can relate that directly to the temperature. Now for a lot of the conditions that we're working with, it's not thermal, so we have to be careful. But even when it's not thermal, you can talk about it as an RMS velocity or a kinetic energy distribution. But I'll always characterize it in terms of temperature. So when it's far from equilibrium and I say temperature, really I'm just talking about the RMS spread of the velocity distribution. So in general, we get a narrow spectrum, it's nice and cold. We get a broad spectrum, we know our system has heated up, the ions at least. Okay, so first let's look at some of our first signs of the breakdown of this classical weakly coupled plasma concepts. So that came really from our first observations of the system, where we noticed that the ions heat up drastically during the first 100 nanoseconds or so. And when we first saw this, we were kind of surprised. We'd worked really hard to make very, very cold ions. The ions should have the kinetic energy distribution of the atoms from which they come. So that should be down in the millikelvin regime. But we see them heating up on the order of a Kelvin or so. And where this is coming from a phenomenon that's been called disorder-induced heating. And what's happening is that initially the ions have very little kinetic energy, but they have a lot of potential energy. They're in a configuration in which we've sort of suddenly turned on the Coulomb interaction by ionizing them, and some of them are too close to the neighbors and some of them are too far away. And we're watching the system roll down a global potential energy surface towards the minimum, and that potential energy turns into kinetic. So actually, we don't see it directly, but while this is happening, short-range spatial correlations are developing. And it turns out that the amount of energy released per ion is about E squared over interparticle spacing. And the time scale on which it should happen is actually given by, can be related to a very important or fundamental frequency or time scale in the plasma given by the plasma ion oscillation frequency. This is the frequency of short-range ion density fluctuations. And if we rescale our data by these parameters, they both just depend on density. We get universal curves. It really shows this is the physics that we expect. It really is happening in there. Now, when this is equilibrated, we know the temperature of the system, and we know the density by looking at our images, and that's all we need to know in order to ask ourselves or calculate the Coulomb coupling parameter and determine if our systems really are strongly coupled. And so what we see is that the Coulomb coupling parameters, the ratio of the potential to the thermal energy, always comes in between about 2 and 4. No matter what we do, we change our densities by almost 2 orders of magnitude. We change our temperature by at least an order of magnitude or maybe a half, and we always get gammas that are about the same. And this actually makes a lot of sense. You start out with all potential energy and no kinetic energy, and after it equilibrates, roughly you get about half potential, half kinetic. That's gamma about equal to 1. And the details of how the electrons get in there and do some screening makes it be a little bit larger than that. So this disorder-induced heating is kind of like a feedback mechanism that always gives you gamma on the order of this range. Now that's actually going to come back to be important later on, so don't forget about that. But it's also kind of an interesting observation. But the good news is that it equilibrates with gamma greater than 1, not less than 1, so our ions are strongly coupled. They're in the liquid regime, not the solid regime, but they are in this regime where we expect things to behave a lot differently due to the establishment of these short-range spatial correlations. So we can add ions in an ultracold plasma to this pantheon of strongly coupled plasmas. Now, another thing that very quickly that shows even more breakdown, more exotic behavior that's only coming about because of the strongly coupled physics is if you look really closely, you can see the kinetic energy actually oscillates. It overshoots and oscillates before it settles down. And this comes about because when you're in the liquid state, your charged particles are actually caged. They can't move so freely past their neighbors. It's kind of like a liquid where the particles are going to shimmy around in this little potential created by their nearest neighbors. And so as an ion rolls down the hill, changing potential energy into kinetic, it'll roll back up the other side, changing potential energy, the kinetic energy back into potential energy. So you get a little bit of this oscillation. It's heavily damped, but this is the phenomenon that's going on. You can think of sort of an egg carton kind of potential, although there's not really long-range order in the system. And the frequency of this oscillation, at least qualitatively, seems to match this ion plasma oscillation frequency. Now, to really emphasize how bizarre this really is, what we're seeing is this oscillation is the equilibration of the two-particle distribution function. And the approach to a constant temperature is the equilibration of the one-particle distribution function. And most of the time, we're used to saying the two-particle distribution function equilibrates very, very quickly. We forget about it, and then the one-particle distribution function equilibrates. That's how we can truncate the Boltzmann equation and do a lot of nice statistical physics that way. In strongly coupled plasmas, actually, there's only one time scale left in the system. That's the ion plasma oscillation frequency, and everything happens at the same time scale. That's why we see this really exotic equilibration dynamics. So really, this is really coming about only because we're in a strongly coupled system. Now, that same kind of dynamic should be happening in all the other laser-produced plasmas as well, but it's really hard to see them in these systems because the densities are so high that the time scales are very, very fast. So what we get by working with ultracold atoms and ultracold plasmas is we slow those time scales down, and we can actually see these phenomenon because we're working at lower densities. Now, there are, as I said, these other phenomena, they should be happening in these systems as well. And while experimentally, it's quite hard to see them because of the fast time scales, you would think that through theoretical probes or molecular dynamics simulations, you could have seen that kind of behavior. And actually, that is the case. And in the context of looking at of where I want to go next, the next topic, which is looking at the kinetic energy oscillations during equilibration as a real probe of the damping and dispersion of the ion motion. And so the motion of the ions in plasmas like I talked about before, the inertial confinement fusion pellets, fast pulse lasers hitting solid targets, has actually been studied for decades from a theoretical standpoint through molecular dynamics simulations. Also liquids, the same kind of phenomenon are happening in there. Through these molecular dynamics simulations, people have looked at the way the ions' motions are damped and the kind of collective modes that occur in these systems. And they, if you look at it a certain way, they get plots that look like this. So what's plotted here is something called the autocorrelation, the velocity autocorrelation function. So this is just a first order correlation function in time of the velocity of individual ions. And of course then you average over all the ions and you average over the initial time to just get a function of the time difference between your, the velocities. And if you normalize it, you get plots that look like this. So here's a nice system. It's actually a classic paper, very highly cited, that looks at the velocity autocorrelation function as gamma in a system changes from 1, so that's relatively weakly coupled, to a very strongly coupled system. So going from a gaseous system to a solid system. And you can see these oscillations and wiggles coming in just exactly like what we have. So that suggests you must be looking at some of the similar physics. And really, it makes sense that you should be, because this function is basically saying what's the memory time for the motion of ions in the plasmas or in the system. If there's a long memory, you expect a slow decay of the velocity autocorrelation function because there's some correlation in the motion that lasts over time. or if there's some collective motion so that the velocity pattern is changing from positive to negative through time, you would expect these kind of oscillations. So these are telling you about the collective modes in the system, which is exactly what we're seeing here. The kinetic energy is, in order for it to oscillate like this, it's saying that there's some correlation in the velocity of the particles. Now there are important differences between this function and what we're measuring. For instance, this is actually an equilibrium property of the system. You do it in thermal, you let your system come to thermal equilibrium, and you're averaging over time, so it has to be an equilibrium property of the system. Where here, we're definitely starting out of equilibrium. So there's some differences and some similarities as well. But there's very interesting things that are happening here. For a gas, you see no oscillations. That's because the particles are really just moving in straight lines, and you can model it kind of like on a time scale of the collision, your velocity gets randomized, and that leads to an exponential decay of the correlation function. Whereas as you get to liquid and then solids, you've got more of the collective modes, the oscillations happening, and the very strongly coupled form might suggest some kind of velocity that has a damped oscillator type form. So this form is actually very interesting to me because it actually, as I'll show in a minute, it matches and can fit my data pretty well. So there's definitely some match that can go on there. Now usually you'll take those kind of autocorrelation functions and take the Fourier transform and get the power spectrum, and then really look at the spectrum of your excitations in the system. And here's another paper for a little bit more recently that shows as gamma increases, you get a strong peak that shows up at frequency equal or pretty close to the plasma oscillation frequency for the particles in the system. And the implication that people tend to draw from these is that the thermal motion is coupling to the collective motion of the ions. So these kind of mode structure is telling you about the frequency of the collective modes, and then the damping rate is telling you about the damping of these collective modes, which are very, very important things to understand for a system. In particular, you can directly relate these velocity autocorrelation function to the viscosity of the system through fundamental relationships. So our question is, do our kinetic energy oscillations access the same information in the plasmas? So here's some very, very recent data where we've improved our ability to resolve the oscillations in the kinetic energy much better. So we can look at small regions of the plasma without any density averaging, and we can look at good temporal resolution as well. And you can clearly see these damped oscillations. And now we have enough wiggles on the spectrum to really say something about the damping. And now the damping really has to come from intrinsic properties of the plasma. There's no density averaging going on in here that would be changing the frequency to lead to just dephasing of the motion in our probe. We're really looking at, on a microscopic scale, how are the motions of the ions changing. So if we go from an inner region to an outer region, you can see, for instance, the frequency of the oscillation gets a lot slower as the density drops. That's what you expect for the motions in this lattice. If the density is lower, then the oscillation frequency in the lattice should be lower as well. And we fit these curves to this damped oscillator expression as well. And the main fit parameters are the frequency of the oscillation and a damping parameter. And the damping parameter I'll put in units of time scaled by the inverse plasma ion oscillation frequency. There's also an overall scale of the energy that I don't have time to talk about, but you can predict that from fundamental relationships as well to get the amplitudes of the curves. So here's what we typically will see for the oscillation frequency in our data. So here I plot the ratio of the frequency to the ion plasma oscillation frequency, and we see that we always get a little bit greater than 1, maybe 1.1 or so. And there actually is theory for what the oscillation frequency should be, assuming that what we're exciting are the ion plasma oscillation modes. So these are the dispersion relationships. So we can start to make some statement about what dispersion relation is describing our plasma. And actually, there's a crossover right as you go into the strongly coupled regime. This is what I meant when I said, as you get strongly coupled, things are really changing. One of which is the dispersion relation. For a weakly coupled plasma, the dispersion relationship for the ion modes actually should be positive. Larger k vector for your modes should increase the frequency. And this comes from standard plasma theory. Whereas if you become strongly coupled, you actually expect your frequencies to have negative dispersion and becoming lower frequency as your k vector increases. This comes out of more of a semi-empirical with a lot of input from the molecular dynamics simulations. So we're actually right in the crossover of this region, so it's not too surprising to expect that our gammas are just about on the order of, our frequency ratios are just about on the order of 1, where we're seeing the crossover. So actually, this is where I really wish I had a knob that I could tune my gamma, my strong coupling, a little bit more. That's one of the ways, one of the things we're working on now, to be able to vary gamma so that I can explore one of these other regimes. So right now, we seem to be right in the regime where it's crossing over from one to the other. And we definitely have some fitting factors on the decay factor, although this is still relatively recent. We're working on figuring out how to relate it to the other things that have been done in the literature previously. But it's a pretty strongly damped oscillation, and the time scale for the damping is about on the order of the ion plasma oscillation frequency. But as we go to more weakly coupled, we should see much more strongly damped oscillations, and as we go to more strongly coupled, we should see less damping. So these are the kind of physics I think we can really study with the ultracold plasmas and be able to observe some very interesting crossover from the weakly coupled to the strongly coupled behavior. So now I want to transfer to another topic that's related to these collisions between the ions, but looked at in a little bit different way, and still is going to tell us about what happens when we get strongly coupled. And that's looking at something called the Landau-Spitzer time in the strongly coupled plasma, which relates to the time scale on which the velocity distributions equilibrate. So often in plasmas, you get different temperatures for different populations of your particles. For instance, in laser-produced plasmas, the energy tends to go into the electrons. So you have a very hot electron gas, and you want to know how quickly it equilibrates with your cold ions, for instance. And the rate of energy exchange and the relaxation to equilibrium of your system is very, very crucial to understanding the properties of your system. For instance, it can be crucially important if you're trying to get inertial confinement fusion to go. All your energy goes into the electrons. Here's a simulation that gives electron temperature and ion temperature for a dense hydrogen plasma. You put all your energy into the electrons, but you want it to get into the ions because you need your ions to collide to drive fusion. So this thermal equilibration rate will tell you whether you can hope to get critical conditions for fusion in the National Ignition Facility or not. So these simulations were actually done at Lawrence Livermore, one of the largest computers in the world, to try to figure out what the thermalization rate is in these plasmas. And what's interesting is because these plasmas can get into the strongly coupled regime, the normal theories people use to explain these equilibration rates, they break down. There are problems with them that I'll talk about in a moment. So it's really an interesting question as to how these rates behave in this strongly coupled regime. That's why people have put so much effort into trying to study them. And for instance, here's a paper, PRE, in which people took the classical Landau-Spitzer formulas, which are these ones that do crazy things and diverge, and tried to figure out what kind of corrections you would have to do to make them work into the strongly coupled regime. And I'll talk more about these kind of curves in a moment. But a lot of effort goes into trying to understand these systems. Now, the reason why it's not so trivial to understand the collisions in these systems is because we're dealing with Coulomb collisions. We're kind of used to, in the cold atom community, dealing with these nice short-range collisions, and they're actually really easy to deal with compared to Coulomb collisions. The Coulomb potential with that 1 over r causes a lot of problems because it's so long range that essentially particles are interacting at any distance. You have to take into account all these interactions to describe your particles correctly, and it makes it hard to describe a cross-section. So typically, you use an argument that I'll describe in a moment called the Landau-Spitzer argument, and it assumes the predominance of very long-range collisions that cause very small angular deviation in the particles. You assume the particles are pretty much moving in straight lines and just deflected a little bit due to the collisions with particles. And so you can look at the rate at which this perpendicular velocity essentially diffuses. As you get collisions of different directions as you go through the plasma, the perpendicular velocity will sort of do a random walk and diffuse. And the rate of growth of the RMS perpendicular velocity for some test particle is the important parameter you want, and you would expect to find it by integrating over all impact parameters, because it's interacting with all the particles in your plasma. But if you do that, as you extend the integral to infinity, the rate will diverge, the rate of growth of this perpendicular velocity, just because it's a Coulomb collision. So the way you typically handle this is you put in some arbitrary cutoff in the integral. You say, well, I'll only integrate up to some finite range, and then my integral won't diverge. And you make some argument for why you can cut it off. And in the case of a plasma, you argue that you can cut it off at the Debye length. Now, we've already heard the Debye length, and I'll explain in a moment, but essentially you say outside of a certain radius, you don't interact with those particles anymore. So the Debye length comes in from the idea that particles, charged particles will screen the interaction or the Coulomb potential from each other within the plasma. It has many different interpretations. It's the distance an external field will penetrate into a plasma before particles rearrange to screen it out. It's the length scale which divides single particle from collective particle behavior in your plasmas as well. And it's also the length scale over which the field of an individual charge, say this red one, that normally would have a Coulomb potential, would get screened out and changed into a Yukawa type potential because all the other particles will just slightly rearrange themselves to screen out that, that field at a larger distance. So a very important parameter. It depends on the temperatures and densities, and if you have multiple components in your plasma, both components can contribute to screening. You need to be a little bit careful about the time scales on which particles can respond. But we're going to be talking about the ions, so they move slowly enough that other ions can screen them as well as the electrons. So this is the expression to use then. And because our ions are so cold, you actually get your screening determined by the ions. They are the dominant mechanism. So when you put in those assumptions of the Landau-Spitzer theory with that cutoff at the Debye screening length, you can get the time scale for velocity equilibration between different populations in the plasma. If you have the rate of change of the temperature of one population will be proportional to the temperature difference between the two populations divided by this Landau-Spitzer time. And you get some very interesting behaviors. It goes as 1 over t to the 3/2. This essentially comes from the Rutherford cross-section. The cross-section gets bigger as the collision energy between the particles actually gets smaller. So that's this 1 over temperature behavior. And it's this log of lambda that reflects that cutoff that I mentioned. Lambda is the ratio of that cutoff distance to this Thomson radius, which we've seen before. Or the Thomson radius also can be viewed as the closest distance that two particles will approach each other if they have the thermal energy and they're interacting with a Coulomb potential. And the cutoff distance is the Debye screening length. So what gets really interesting is when the Debye screening length becomes smaller than this Thomson radius. And then your logarithm will become negative. Doesn't make any sense. Now your time scale becomes negative. So it totally breaks down. And you expect this kind of breakdown to happen when your system becomes strongly coupled. Because I can rewrite these constants for the lambda as going square root of 3 divided by the Coulomb coupling parameter to the 3/2. So when gamma gets to be on the order of 1, then lambda is on the order of 1, and your logarithm goes 0, and then as gamma increases more, it becomes negative. So if I plot the Landau-Spitzer time for different densities and different temperatures, it's going along fine, and then it hits, here's Coulomb coupling parameter equal to 1, and it nosedives and goes and does something really crazy, which can't be physical. So we know there's some breakdown in the strongly coupled regime. And if we look at typical plasma parameters that we can create, we have a coupling parameter, it's almost up to 2. Our Debye screening length is on the order of 4 microns, and our Thomson radius is about 5.6 microns, so we're clearly into the regime where the Coulomb logarithm isn't going to make any sense, and its Landau-Spitzer formula really should break down. So people have made lots of corrections trying to change this cutoff to be something different so that it doesn't diverge. But really, on a fundamental level, the whole approach has to be wrong. The Landau-Spitzer time, it assumes the predominance of long-range, small-angle collisions to calculate the thermalization rate. But in strongly coupled plasmas, you have short-range, very large-angle collisions that are dominating you. Your particles can't move very far before they suffer a big collision. So really, the whole picture should should break down, and we should see some new physics. And that's the kind of physics that we can probe with the ultracold neutral plasmas. So how do we do that experimentally? Well, we have now bring in all the nice tricks we have from atomic physics to this system. Our ground state for the strontium ions is degenerate. We have a J equals 1/2, so we have minus a spin down and a spin up system. And if we drive it along our imaging transition with circularly polarized light, we'll only talk to ions that are in the spin down state. Of course, we'll pump them up and then they can decay to other state, so we can optically pump them to the other state. So that's kind of nice. We can change the distribution of levels, and we can selectively probe the population of the different levels. And if you remember when I talked about our probe, it's Doppler broadened. So we have the ability to do this in a velocity selective way. We can talk to just one velocity class and change the distribution and interrogate the velocity distribution later on. So here's kind of what we can do experimentally. If we start with a system with equal population, spin down and spin up, and we drive with the sigma plus light, what we'll do is we'll create a little bit of population imbalance with a extra population just in this velocity in the spin up and a decrease in the spin down. Of course, then if we turn off our laser and allow collisions to occur, they'll mix all the velocities and the system will rethermalize, and we can now see a new velocity distribution in which overall the spin down is a little bit less and the spin up is a little bit more. And these processes we can really see. How much more time do I have? 5 minutes? Okay, I'll go. Well, so the timing of the experiment then is shown here. So we apply a magnetic field to define our quantization axis, and we apply our pumping beam as intense as we can get it to create the population imbalance. And then we'll turn off that pump and let the system evolve for a while. And then we come with a probe beam that's independently tunable and map out the fluorescence spectrum or the excitation spectrum of the plasma, which we can map directly onto the velocity distribution, but it's only interrogating this one spin state. And here's the kind of data that we see for a typical plasma that's just barely into the strongly coupled regime. So just after the pump beam has been turned off, we can clearly see the feature that's left over in the spectrum. And as I remind you, this is essentially population versus velocity. So without any pumping, we see a nice Doppler broadened line shape. And after pumping, we've certainly lost a lot of ions because we pumped them over to the dark state. But we can clearly see a feature that's giving us a lot of information on what velocity class we pumped and what the current distribution is looking like. And now we let time evolve. So here's the population imbalance that I talked about. So it's still equal for this velocity class, but a population imbalance for this velocity class. So we let time evolve. We can see that this velocity feature is starting to fill in. Collisions are redistributing the velocities and making this feature go away. And we go a little longer, we can see the feature is pretty much gone. But actually, interestingly, the feature tends to fill in faster than the overall shape of the velocity distribution moves over. So sort of this is now, I think, getting to real interesting kinetics in the plasma that's a little bit beyond what my theory knows how to handle. But I think there's really interesting stuff that we're able to see here. And then on a much longer time scale, you can see that the velocity distribution now exactly mimics the original velocity distribution because we really haven't changed the temperature of the plasma once it gets back to equilibrium. So when it comes to equilibrium, we should see the same temperature distribution. Everything should center back up again. There's just extra population in the dark state, and our bright state has dropped down a lot. So this gives us a lot of information about how the velocity distribution is changing. And we see great differences as well. If we look at a system that's lower temperature, lower ion temperature, more strongly coupled, pretty much the same density, you would expect from normal scaling that at lower temperature you get faster collisions, faster thermalization, and we actually do see that. It's a little harder to get a significant feature on the velocity distribution because there are collisions going on while we're pumping, and it's hard. We go as fast as we can, but those collisions are pretty fast. And then even within 50 nanoseconds, we can see pretty much that feature is all gone. So you can see that the collisions are much faster just by lowering the temperature a little bit compared to this system. So really sensitive to the dynamics in the plasmas. Now, we have a very simple model to try to quantify what's happening for this thermalization rate. Essentially, sort of a simplified Boltzmann type equation with maybe the simplest collision integral you could possibly have, where we look at the population of the different sort of magnetic sublevels and the different velocity classes, assuming that a collision completely randomizes the velocity, but overall the collisions are tending to return you to a Maxwell-Boltzmann distribution. And the time scale for collisions is the parameter we want to fit, which we expect is something that should be mapping onto the Landau-Spitzer, the inverse of the Landau-Spitzer time. So if we run this model with just the fit, really the only fit parameter we have is this collision rate, we can fit all the data pretty well. So this, the black is with no pumping beam on, so that sets the temperature of our sample. And then immediately after the pumping beam, we can see that we've dug a nice hole in there, we fit it, and as time goes by, we can see that hole fit in, and then you can actually see that the distribution is shifting over back towards center as well. So these fits are certainly a good first order approximation of the dynamics, allowing us to get at this collision frequency. And now if we take our measurements and put them on a plot of the thermalization rate versus density for various temperatures, we can see how the regime in which we're studying the parameters and the various Landau-Spitzer times. So you can really see we're off the chart here. Landau-Spitzer times are clearly invalid, and we're seeing that the rate continues to increase while the Landau-Spitzer rate is telling us nonsensically that it should be going down. Interestingly, the Landau-Spitzer rate kind of becomes nonsensical right about where it matches the red line, which is actually the ion plasma oscillation frequency. So physically, it kind of makes sense to me that at really strongly coupled systems, you would expect the time scale should go to the ion plasma oscillation frequency, because again, that's the only time scale left in the problem, and that's the time scale which the ions are oscillating, and that's the time scale which they should come and bang into their nearest neighbor. So it doesn't surprise me that we're kind of following that behavior, although this is preliminary and there's a lot more work to be done to really see how that pans out. Now, unfortunately, we can't explore a lot of gamma space or Coulomb coupling parameter. Here's the same data plotted versus Coulomb coupling parameter. It's a little hard to see, but here's Coulomb coupling parameter of 1 running up to about 4 here. And on the same axis, we have the two different temperatures, the colder temperature and hotter temperature. We really only can vary between gamma of about 2 and 4, so we're out in this regime. And we're currently working on ways to allow us to actually decrease our Coulomb coupling, so to connect back down to the classical formula, because that'd be really nice to be able to sort of plot out how it goes from one regime to the other, and that's where we're going. But I already think that we're seeing some really exciting things, being able to talk about how the system behaves and how it equilibrates into the strongly coupled regime. So with that, I will conclude. Ultracold neutral plasmas are a wonderful system that's allowing us to explore new regimes of plasma physics. And a lot of the experiments I've talked about before, but not today, are the expansion and recombination and collective modes of the various components. And today I've talked mostly about how strong coupling modifies the traditional plasma concepts, such as equilibration, kinetic energy oscillations, and the things that are related to velocity diffusion and equilibration in the system. And in the future, as we learn how to vary the coupling of the ions away from this gamma about 2, we should really be able to map out how all these things behave and cross over from the weakly coupled plasma physics that's somewhat familiar into the strongly coupled regime. So with that, I will thank many graduate students present and past, and undergraduates and postdocs who have contributed to this experiment, and I thank you for your attention.
Tom?
So do you think, Tom, you burn a hole for ion moving in the plus z direction. Do you think there's any hope of seeing that hole be reflected when they bounce from the nearest neighbor and coming back in the minus z direction?
Yeah, that's a great idea. I don't think so. I don't think so, because well. No, I think you're right. I think you're right. If I really think of it as I'm looking at the ions, it depends on whether the thermal motion is dominant over the oscillation. But if it really is, they're oscillating like this, I think in principle it could be, if we could resolve that time scale and get enough signal to noise, you might hope to see a little bit of rebound, possibly.
Another question? Back there.
What's the electron Debye length compared to the interparticle spacing?
The electron Debye length is around 30 microns for these conditions. Interparticle spacing is around 6 microns, and then the Debye length for the ions was around 4 or 5 microns.
It would be interesting if you could get the electron Debye length down towards the interparticle spacing, because then the electrons start to shield, and it should start to change some of the fundamental frequencies that you're seeing.
Yeah, I think you're absolutely right. It's very interesting. I think when we do that, then we run up to the 3-body recombination that Steve. So Whether we can do it on a time scale and still see it, or whether there's a fundamental limitation, I think when these experiments first started, there was hopes that we can get electrons and ions both really strongly coupled, and nature seems to be telling us it doesn't like strongly coupled electrons. It wants to turn them into Rydberg atoms.
Okay, Francis.
In the two experiments, you sort of had a damping time from the oscillation of the kinetic energy, and now you have this damping rate from this other measurement. How do those compare?
Right now, all my time scales are the ion plasma oscillation frequency.
But this seems to be a big multiple of that, or no? So they're about the same.
Yeah.
And because the alpha was.
You might say, if I had to say, I might say that this is a little faster,
Okay.
and the damping is a little slower,
Right.
by factors of 2 or 3.
But each way, so the damping was sort of slower by a factor of 2.
Yep.
And this seems to be faster by a
Faster by a
factor
factor
of 2.
of 2. So
So they're not.
they may not. I don't think they're exactly the same things. Yeah.
So do you see any dependence on the electron temperature of this rate?
Not that I can comment on right now. We haven't taken data varying that. We easily could, but
Electron temperatures.
yeah.
Any more questions? Yes.
Perhaps it's related to Tom's question a little bit. I mean, is there anything to suggest that something different happens when you get to the boundaries, so that you have a faster rate on the edges than you say you would in the middle of the plasma, or do you expect things to be sort of pretty much the same as you go through?
So if you're talking about boundaries of the plasma, the whole plasma, we don't expect ions to be traversing the whole plasma. They'll be localized. Actually, when we take our data, we have with the fluorescence, we're actually looking. We can resolve center of the plasma versus edge of the plasma, and everything seems to make sense. It just scales with the density being a little different out there, or the temperature being a little different out there. But other than that, it just looks like the same type of physics inside and outside.
That's probably related. So did you do any position-dependent optical pumping and see if stuff moves around?
I guess short answer would be no. I mean, certainly we don't have much hopes of being able to push things around physically. As you do change the frequency of your pumping beam, you are pumping different parts of the plasma. We didn't talk about the expansion much, but actually if you far detune, you'll be in resonance with plasma on the outer edge that's been Doppler shifted into resonance because of the expansion. So we can pump the inner region versus the outer region, and it's preliminary, but it all looks the same to us. It just varies with the density because there's lower density out there.
Okay, so if there's no more questions, the late afternoon session starts at 4. And let's thank all the speakers again.